on this computer. All right, I'm recording, but I guess you guys are going to edit this anyway. So, all right, so
Awesome. Thank you guys. Welcome. Hello, and thank you for coming to ROS Lecture number 2. I don't need that in the back right there. This is also being run by Dr.Shue, and I'm just gonna give it off to him. So
all right, thanks. We're back this time with a more complete PowerPoint and working demos. So first thing that I've got on the slides is a QR code. This has a link to a GitHub page that has the slides hosted there, along with the Python script that I'm going to show at the very end. I've got a few other links in these slides as well, so you can reference the material that I go through on here. So I guess if anybody wants to grab that, I'll give you all a second. But of course, it'll be on the recording as well. So and then these are social links that Cardell sent me to put in these slides. I guess these go to the IEEE student branches stuff.
The information for IEEE student branch Discord, Instagram, and the YouTube these videos will be posted on.
Okay, cool. So we have those, and then finally we have an attendance QR code, so you can check in to prove that you were here to whoever it needs to be proved to. We'll leave that up there for a second. Oh. Okay. I'll see if that's enough time. If anybody missed these, I can scroll back to them at the end of the talk. So I want to recap real quick what we talked about last time very briefly, and then we'll get into our new content today. So real quickly, what is ROS again? So ROS is it stands for Robot Operating System, and it's a collection of software packages to make building complex robotics applications easier. And it makes it easier by standardizing a lot of different things in robotics. We mentioned last time robots come in a lot of different shapes and forms, and so even like you can have things that walk on legs and roll on wheels or fly, but a lot of them still care about a lot of common aspects, like just what is their velocity as they move through their environment, regardless of whether that's being achieved through flying or walking. They have a lot of things that are in common. And if we focus on those sort of common aspects, then we can design our different algorithms and software packages such that they're more robust and portable. And ROS really helps achieve that by creating standardized interfaces for these algorithms, and then also provide a messaging system. So the messaging system is achieved through sort of what this diagram has here, where you have a ROS master that facilitates communication between different nodes. Nodes are individual programs that run on the robot. Robots often are comprised of many different programs that are running simultaneously. Like you have some program that might be interfacing with a sensor and doing some maybe image processing to then give you maybe like depth information about what's in front of the robot. And then you might have a mapping algorithm that's a separate program that's running, and it wants that depth information. And so we can pass that along through ROS messages through what we call a topic. And so maybe you have a topic that's called depth image, and then it has that data that comes across it. And so any simultaneously running application that wants that sensor information can subscribe to that. And so we end up with a structure sort of like this, where you have one node that is like the example I just described. It's publishing laser scan information onto a topic called scan. And then we have another node that's subscribing to that and then taking that information and processing it. And so these topics are all some sort of standard message type, like here for laser scans. And I mean, shrunk down too far to really notice or what is actually going on there, but it's a standard structure that all laser scans have to adhere to in order to follow the laser scan message type that this topic in this example is using. So it's all about standardizing things so we can have a common mode of communication. So before you can do anything that we're going to talk about today, you're going to need to install ROS. And so I've dropped some links here on these slides for if you were wanting to install ROS. Basically, all these just link to the installation guide. It's pretty easy to install. It's basically just a matter of copying and pasting a bunch of commands into a Linux terminal. However, ROS 1 only runs on, well, doesn't only run, but the standard operating system to use with ROS 1 is Ubuntu. And ROS 1 is sort of at its end of life, even though it's still widely used by a lot of researchers and people in robotics. It's being replaced by ROS 2. ROS 2 has some new features, but still operates a lot of the same concepts. So our newest version of Ubuntu is 22.04. That's its long-term support version. And ROS 1 is not officially supported on that version of Ubuntu. So if you want to run anything that any of the examples that we are doing in this lecture, you're going to need one of these versions of Ubuntu here. I'm running 18.04 for these examples. But you can install it on basically any of these into the last 4 releases of ROS. So let's talk about the ROS workspace. So after you've installed it and you're wanting to use it, and it takes a little bit of time, so unfortunately we can't really do that today. But I've already got a workspace configured and everything. But we need to understand the structure a little bit before we can start writing code with ROS. So ROS wants to organize all of its code and everything into packages. And so it kind of follows a structure like this diagram indicates here, where we have meta packages, and inside of those packages, or the meta package, you have different packages, and those packages can contain things such as new message types. It says codes miscellaneous, but basically your executables that you run are also stored in packages as well. So everything's just kind of organized into individual packages, which then contain different things inside of it. We'll get a better idea of what those things are as we move forward. So we need to organize things into packages so that way, whenever we build them, they'll be recognized by basically ROS itself, and then we can use this command called ROS run to spin up our nodes and have those individual programs execute. To build ROS packages, we use a build system called Catkin. And Catkin is its own separate kind of tool that has a workspace that is organized sort of like this, where you have your Catkin workspace, and inside of that, you've got several different directories. One of those directories is the source directory, where inside of source, you have your different packages that you're going to build. And inside those packages, you kind of see sort of what we saw in that diagram earlier, where you have different directories inside of that then hold different things that we're going to see some examples of later on. A few of these just to highlight, we're going to be adding things to the scripts portion of the packages because we're going to be coding in Python today. So we're going to populate the scripts directory, but these other directories have different things like messages. You can create new message types that go into packages. And then also we'll be running some launch files as well. Launch files are scripts that will then launch multiple ROS nodes. ROS also uses C++ a lot, and so Catkin will also build C++ files. And so you have like a source directory as well, where you'll store CPP files if you're working in that language, but that's not going to be relevant today. So once you've got a package in your Catkin workspace and you want to build it, it goes through this process where it reads everything in the source directories. It'll build those packages into a build directory temporarily. And then the final result gets stored into this DEVL, which I assume stands for development directory. Maybe I'm wrong on that. I did not see anybody explicitly say what that stands for when I was creating these slides. And we'll see this as we move forward as well. So before we do anything, what we have to do is create a Catkin workspace. And we do that by creating a directory. So here I've got the commands for creating the directory and initializing it. So what we have here is the bash commands for making a directory, and then where you move into that directory with cd, which is change directory, and then we call catkin make, which then creates the build process. And then once you set up the directory, you then have to run the a setup.bash script will be created, and that's going to live inside the develop or the devil directory that we mentioned earlier. And whenever you run that setup, then everything that you build inside of your catkin workspace will be sort of made known to ROS, is probably the best way to describe it. So that way, whenever we type ROS commands, our packages will show up as possible targets for those commands. My intention here is to kind of just go through an example as well. So let me flip over to my virtual machine. So let's just kind of expand this and just sort of go through it. So if we look here, I'm in my home directory, and let's see if I can't. Can everybody see that okay enough? All right, cool, thanks. So in here, I've got actually two catkin workspaces already set up. The one that's kind of under the default name that the ROS tutorials will take you through, and then one that I created while I was prepping this talk. So what I'm going to do is I'm actually just going to blow away my sort of example one, and we'll just kind of make that from scratch. So we'll remove this. Let's make a we'll say mkdir, and we'll make I'll just call it, I'm going to use a short name because I'll have to type it a lot. So we'll call it CKWS for catkin workspace, and that'll be the one that I temporarily use for these examples. So we'll make that, we'll move into that directory, and then now I'll call catkin make. And it's going to just kind of go through its build process. There's nothing in it right now for it to build, but it'll still just kind of go through the motions, and it'll generate a lot of those directories that we saw in the catkin structure earlier. So now if I look in this, if I type list, we'll see that there are now 3 different directories that have been created. We've got that build, devil, and source. So now we've got our catkin workspace established, and we can start creating packages. So let's go back to the slides. So to make a package in your catkin workspace, we'll need to go into the source directory, and we will run this line here. For the examples that I'm going to use, I'm going to create a package called, and I already have one that's called beginner tutorial, so I guess I'm going to name mine something different than what's in the slides. But you have this the command catkin create package, and you give your package a name, and then after that package you list dependencies that you want that package to have. Often these dependencies are build tools or message types that you're going to use. So for the examples I'm going to go through today, we're going to use standard messages for the initial introduction. Standard messages are basically messages that just have basic data types in them, like integers, floats, strings, etc. And then I'm going to include geometry messages, which are going to have things like twist commands, which are how we're going to command velocity that we want, like our robot, to carry out. And then we'll also have sensor messages, so we can read things like the laser scan. And then we're also going to add ROS.py as a dependency because we're going to be writing in Python. So yeah, let's flip over and make that package. I'm losing my mouse. There it is. So I'm going to move into my source directory, and then I'm going to say catkin create package. We'll call this I'll call it workshop, I guess. And then we'll say it depends on standard messages, geometry messages, sensor. I wonder if it'll autocomplete. Doesn't look like it will. I can't wait to misspell something and have a made-up dependency. I think I did everything right. So we'll hit enter here, and now we'll see in this source directory, another directory called workshop has been created. And so inside of workshop, we'll see that we have another source directory and a package in CMake list here. So CMake list is a script file that's used for building projects, and Catkin uses CMake. We'll take a look at CMake here in a little bit. So now that we've done that step, jump back to the PowerPoint. And let's move on. So now that we have created our package, I guess this step is not entirely necessary along the way, but we can go ahead and if we were to call did I mention this over here? I think we would have to catkin make one more time. Let me do that. So I'm gonna say here, say catkin make. It's going to rebuild, and even though there's nothing in our package right now, it's going to recognize that we have a package called workshop. And now what I'm going to do is I'm going to call source, and inside of the dev, we have dev directory, there is the setup. Where there should be. Oh, sorry. Source dev/setup.bash. There we go. And so now once I've ran that, now the sort of ROS system is aware of my package's existence. So I can use this command called ROS-cd to quickly move into my workshop directory. And so now we're in my workshop package. And we can then start putting some scripts in there. So let's back over here. So now what I'm going to do is, if I want to create a Python script, I'm going to need to make a directory to hold the scripts, and the package needs to have a directory called scripts. So I guess you could override it, but this is the standard. Is if you're going to have Python scripts, they go into a scripts directory. And inside of that, then I'm going to create a Python script. Where are we? Okay, so we'll come here. We'll say mkdir scripts, and then we will go into scripts, and then we will make our example script called talker. So now we've got a script called talker, and then I'm just going to open this in a text editor. I'm going to shame myself and use gedit instead of something cool like Vim, or I used to use Nano, but I haven't used Nano in so long that I don't remember any of the commands. So a little bit of recorded public shame for myself, but who am I here to impress? Okay, so now we've got our script, and what I'm going to do is I'm going to populate it with this text, and then we will talk about it. And I don't have that in a copy pastable. Actually, I lied, I do. On a different window, let me grab this guy. So this is the talker. And so I'm going to go over here, and I'm just going to put the talker in there, and then we'll save that, and then I'll close it. And then we will kind of examine the code that I just put in there. All right, so just for completion, we've got the whole code that we're going to put in here. What this talker script is going to do is, this is a simple node that is going to just spin up a simple topic called chatter, and then it's going to publish some string on that topic periodically. So these Python scripts that we're using with ROS, at the top of each script, we're going to have this little line of code here, and this is just, it's not really a line of code because it's commented, but basically this is just a ROS Python ROS node declaration that goes to the top of each of these Python scripts. And underneath that, then we'll have the actual, I guess, the more important aspects of this, where here we're going to import ROSPy. So that's our Python or ROS library for Python. So that gives us access to doing things like creating nodes and subscribing to topics and publishing to them. So it gives us access to all those ROS interfaces. And then we're going to import as well different message types that we're going to use. So here we're going to say from standard messages dot message. We're going to import string because that's what we're going to publish on this with this talker node. Then inside of this code, well, I think I've skipped over it a little bit, but down at the bottom, we've got this line here that's referencing if name is equal to main, and this is where our code's going to begin. And so when our code begins, it's going to go into a try except block here. So it's going to run talker, where talker is kind of like our main loop for this node. So it's in a try except just for safety. So in case, well, whenever we click like Control-C or something to cancel the node's execution, this exception will catch it and it'll kind of clean it up and exit the script a little more cleanly. So talker is the function that's really running what we want our code to do. And so inside of this, we've got the first line of code, which is where we're creating a publisher object. So we have pub is equal to rospy.publisher, and inside that publisher parameters, we have the name of the topic that we're creating or we're publishing to, what kind of data type it is, and what the queue size of it is. So you have to specify these three things. So it'll publish, you have to always specify a queue size. So we'll be able to buffer up to 10 different messages, and then it'll just send those out. And then we will call next to this our initialize node, which this initializes this script as a node called talker. And then we have this added parameter here. It says anonymous is equal to true. And what this line does here is each node, whenever you make one in ROS, has to have a completely unique name. And so if you start up another node that has the same name, then it kind of kicks the other node off. And so if you say anonymous is equal to true, then what it's going to do is it's going to tack on some extra numbers on the end of your name to make sure that you have a random name whenever you start it. Oh, okay. I guess I missed I guess I reworked that slide into two different ones and missed that. Then after this, we've got a rate. So ROS also wants to publish messages at a specified rate, and so here we can generate that. And here we're saying that we're going to publish at a rate of 10 hertz. And then we're going to go into this loop where the actual behavior exists. So while ROSPy while it's not shut down, it's going to continue to run this. So as long as the node's running, this while loop will continue to execute. We're going to populate a string that says hello world and then gets the time. And then we're going to call the log info, which is going to then print it onto the terminal. And then we're going to publish that string to our topic that we created. And then we're going to call rate.sleep. And what rate.sleep is going to do is it's just going to waste time until we hit that 10 hertz publishing rate. So if you haven't already exceeded it, then rates.sleep is just going to wait until enough time has elapsed that it can redo the loop again and then continue to publish at a 10 hertz rate. And that's the whole thing. So let's kind of go through this. I should have put this slide up earlier because I already went over that. Okay, so building and running this. So to build it as a script, so you don't really need to build anything, but to get everything to sort of go through the catkin process, and so that way ROS recognizes it, we're going to need to add this line to our CMake list. So let me copy that on my end here, and then we will stick this into our script here, and oops. There we go. And we're going to gedit CMake list. And then I'm just going to go to the bottom of this. Their default CMake lists have a ton of comments in here, kind of explaining what a lot of these different lines that you could potentially add does. So it's extremely verbose. For this, the only things that we really need to notice here is we've got our list of dependencies. So whenever we made our package, they were pre-populated in the CMake list. And then down here at the bottom, I'm adding my little bit for my scripts that I want to be included in the catkin build process. So you have to list each one of those here. So we're adding talker. I'm going to save this. We'll close it out, and then we'll go ahead and build it. So, oh, and I almost forgot. I'll need to. These are in the slides somewhere, but I need to go into this script, and I need to give this script executable permission. So we'll say chmod plus X to give it executable, and then target the script there. So going here, we'll go all the way back to our root catkin directory, and we'll call catkin make. And there we go. Okay, so now it's made. And so now what this is going to do is I can now call ROS run, and I can say, so whenever you want to run nodes that you've created, you call ROS run, and then you put a space, then you list the package name, which we said it was called workshop. And then inside of workshop, we've got talker.py. And I've got apparently an error in that first line of code. I guess I'm not good at copy and paste. Goodness gracious. Let's see. That's inside of source, workshop, scripts, and talker. Toggle line numbers. Amazing. That's what I get for copy and pasting with a trackpad over here. Cool. Yeah, this is just the intro script from the actual ROS tutorials. Okay, so now let's try that again. Oh, I had it running a second ago. So this thing is already pre-configured to communicate with my robot that's on the floor over there, and its ROS master node has apparently died. So well, let me actually check a few other diagnostic things. Like doesn't look right. Is my adapter name changed? You are on, aren't you? Doesn't look like. Does this?
No, those don't work.
Who watched me plug this stuff up and just like. Okay, so the router's not plugged in. That's and neither is the brick that provides my. Yeah. Let's give me a thing. I should expect it at this point. Oh, we'll get there. Okay, and then I can plug this one up over here. Yay, all right. I think just yes. Oh, okay, sure. Oh, no, not help. Nobody can help me now. Let's see. There we go. Okay. So let's see if I got my expected IP address. It still does not look correct. Oh, it's thinking about being connected up here. Let me double check might take us, maybe it takes a second since I just plugged everything up. But this feels concerningly slow. Maybe we'll keep that unchecked, actually. Maybe I should have checked it. I don't know if it actually matters. What's actually going to be the real unfortunate thing is if I have to restart this stupid virtual machine. Do you hear that? Yeah, the recording's also jacked up. That's because I just unplugged all the stuff, and even though I'm broadcasting to nobody, Zoom needs to be online. Cool. Hey. Well, presumably for my sake, you would have edited all that out anyways. Okay. Yeah. You know what? I agree. Oh, but let's see. Yes, we got 2, 3, 4. Okay, so yeah, I think we're in business. Let's see if I can't run this now. Nope. Doesn't see it. You stop. It's Yeah, well, I mean, I see the turtle bot. Well, I guess I don't have the actually. Oh yeah, okay, now we do have it's at incomplete. That's what's a little strange, but maybe that doesn't matter. Yeah, I just don't know why it's let's also let me double check the turtle bot as well. Check it started, but I guess it also didn't have a network connection for a while. I don't know how much it cares about that, but I feel sorry for whoever's going to be editing this. Let's see. Let's just real quick, for safety's sake, just reboot this. Let's back up. I'm impatient. You know, while we're sitting here waiting for this, I feel like you know, this doesn't do a lot of the way this appears doesn't do a lot of justice for ROS. It actually does make things a lot easier, but you got to take this with a grain of salt because I'm working with like really old deprecated equipment. So it is a very, very valid excuse. This thing worked beautifully back when 1804 was just the latest and greatest. Actually not 1804, 1404 was when this was last officially supported. Yep, this thing is not. Oh, you know what? I bet it did. This is gonna say Niner Wi-Fi guest, isn't it? Yeah, it is. That's why I can't talk to it, because when I lost the network, it was like, oh, jump on it. Even though I told it only connect to this one. Yes. Okay. I had to kill it. What? Hey, Control C. Maybe it didn't hear that. Okay. All right. We'll let you just sit there in case I have to come back to that. That also broke the recording again. Let's go back to this. Share. There we go. All right. So now we should be able to, okay, there we go. Yeah, so simple. Okay, so something I didn't want to talk about yet, but so the reason I had to have this robot running is because this thing is running the ROS master for these demos. You can only have, well, you can have ROS masters running on different machines, but if you're wanting to have like, say, one machine connected to one robot, only one person could be running the master. So this one's running the master, which needs to have all the messages and things go register with it. So we needed to contact that, even though we're not really sending any robot commands yet, but we're going to. So that's so that was necessary. Okay, all right. So what we're seeing here is this is the log line of code that we wrote in that Python script. So we see it printing this here, and if I open up another terminal here, if I go to ROS topic list, we're going to see all the different topics that currently have data going across them right now. And we see there's quite a bit, and there's a lot because, well, when I start up the Xbox Connects node, it creates a lot of different topics. So all these with camera are related to the Connect. And then down here, all these with CMD vel, these are command velocity inputs for the robot to tell it to move. And if we scroll around, we should see actually it's chatter was our topic, I believe. So there it is. So chatter shows up in the list, and it's this guy publishing to it. And so if I look over here, we can do something like I can say ROS topic info chatter, and we can see some information about the topic. So we can see right now we've got a publisher. It's called named Talker, which we named it in our Python script. It's also got a jumble of numbers after it because we told it anonymous. So therefore it tacked these on to make sure that it's got a random name. And then we can also see what kind of data type it is. So it's just a simple string type message. So that's that. And then we can also say ROS topic echo, and we can see what's I gotta actually say what topic I'm echoing. Chatter. So ROS topic echo chatter, and there we can see the data that's being published to that topic. So there's our little string that we're writing. So same thing that we're seeing over here. And then if I were to stop this node, and we come over here, we'll see that this is also stopped because nothing is publishing to it anymore. So with ROS, it's all about publishing data and then subscribing to data. So the next thing that we'll do is we will set up a little subscriber. Let me go ahead and prepare my clipboard with the code that I'm going to use for my subscriber. And then we'll flip over to the slides. Okay. Back to the slides. So we just ran everything. We just kind of did all that stuff. So now, yeah, building a subscriber node. So it's going to be the same process. We're going to go into that scripts folder. We're going to make the Python script, and then it's going to contain this content. So let's do that. It's going back over here. I don't know why this is still kind of, I'll worry about you later. I can say ROS CD to immediately go into my workshop. it's not sourced in this one. So every time you open up a new terminal, if you want your packages to show up there, you have to go source devel setup dot bash. There we go. And then now I can say ROS CD workshop, and it knows where everything is. All right, cool. So we'll go into the scripts folder. We will make a new script called listener.py. We'll gedit it. And here I thought gedit was going to be the most embarrassing thing I do today. It probably still is. Let's see. So we'll paste our code in there. We'll talk about it here in a second. And then we will, well, before I leave this, I will give it executable permissions. There we go. Cool. And then we'll go back down. I'll also, while I'm here, we'll hit the CMake list to add our new script into it. So we'll just go down here and we'll put a space after our other script. We'll say scripts, and then we'll say listener.py. Save it, close it, and then we will talk about it real fast. This one kind of has a lot of the same structure that we saw before. So apart from like main calling a function, there's just a little bit that we can notice here. Here we've got our listener, and so we initialize the node, give it a name that's anonymous again, and on this this line here, we're going to establish a subscriber to the chatter topic. So we say what the topic name is that we're subscribing to, what that topic's message type is, which is a string, and then we specify a callback function. So this function, we'll see that it exists up at the top. Did I already highlight that? I did not. So this function at the very top that says definition callback data. This function will be called every time we get new data on the chatter topic. And then all we're doing here is we're just logging it to the terminal. So we'll print it all out every time we see new data. And then down here, spin keeps this code running until it's shut down. So this code doesn't have a loop or anything necessary it needs to do, because all it's doing is anything it wants to do is in the callback function. We're just reacting to new data that comes in. So we're just going to stall here as long as it's running. And then anytime we get a message, we call the callback function and print it back out. So let's go ahead and build that on the terminal here. So yeah, I think I added everything that I needed. So we can just call catkin make. I went too far. Let it build, and unless I forgot to check something, nope, looks like everything's good. And let's go back to our publisher that is just not quitting. Yikes. Let's see. I got to source the setup function here. I'll just use this window. Setup.bash. Normally, whenever you have a catkin workspace, you will call setup.bash like in your, so whenever you open up a new terminal, you have a script called .bashrc that will run, and you'll typically take lines like this and stick it in there so you don't have to type this in every time. So let's see. I'm going to say ROS run workshop talker. So we're publishing, and then we'll run our subscriber ROS run workshop. It's called a listener. There we go. And so we're just printing out what we receive on the topics. That every time we see something printed, that's that callback function running and just calling ROS log and printing it to the terminal. So there we go. That's the basics. We can now write programs that can publish data to topics, and we can subscribe to topics. All right. So that's all kind of the nuts and bolts you need to do something really basic with ROS. So the next thing we'll do that's also something basic is we're going to take our Turtlebot here and write what I call the Wanderer program. So we already did all this stuff, so I'm skipping it. It's in the slides for completion. So if you ever want to redo these things on your own, you've got the information there. So what the Wanderer robot is going to do is going to be a very dumb application where we're going to take our robot and we're going to just let it drive around semi-aimlessly, and it's going to try to not run into obstacles. And so to achieve this, what I'm going to do is we're going to use the Connect to get information about what's in front of us through its spoofed LiDAR topic. So what it's going to do is it's going to take its depth map, take a small slice of what's horizontally in front of it, and then take that distance information about what's in front of it. And if there's nothing in front of us, we're going to just drive straight. And if there is something that comes within, I think I have it set for like less than half a meter in front of us, then we will just turn to the left or something. And so we'll turn for a small amount of time, and then we'll just start driving straight again. So theoretically, it should just bounce around kind of like a Roomba in your house. So the code for this looks like this giant blob. We're going to highlight a couple of important aspects of it. At the top, we've got new messages that we're importing. So here we're pulling in from sensor messages.message, the laser scan message type, which is going to give us this 2D sweep in front of it. And then we're going to pull in the twist message type. Twist message is going to allow me to publish velocities that I want this robot to carry out. Since this is just a simple differential drive based like robot, that means it's just got two little wheels on the bottom that spin. That means I can only really give it two types of velocities I can carry out. And carry out linear velocities, which means it's just driving straight in front of it, or it can carry out rotational velocities where it just turns in place. And those are all centered around different axes. So for a simple robot like this, we just model it as a single point. It's got the x-axis that points out in front of its face, and that's where our linear direction goes. And it's got a z-axis that's kind of coming out the top of its head, and we can rotate around that to turn in place. So that's what we're going to be doing. Same kind of structure as before, where inside of main we call Wanderer. Wanderer sets up a node called Wanderer, and it gives itself an anonymous name. And then we're going to subscribe to the laser scan, and then we're also going to publish twist messages to the velocity or the command velocity topic. So we have a callback function. This callback function is going to be associated with our laser scan. And what it's going to do is it's going to receive that message. And I've got a little for loop set up here. And all it's going to do is it's going to look for what the minimum distance that it recorded was. So whatever the closest thing is in front of us. And then based on whether we have what that distance is, we're going to do one of two things. So inside of the Wanderer, we've got our main loop. So as long as it's not shut down, we're going to create a twist message. And if that distance we see, if there's anything less than half a meter in front of us, the twist message, we're going to populate with a linear velocity of 0.25, and I think it's meters per second. And we'll publish that to the command velocity topic. So we'll move at that speed, but if we do detect that there is a distance less than 0.5 in front of us, then what we'll do is we'll construct that command with an angular velocity about the z-axis. So we'll spin in place. And then I have a small for loop right here where I'm just kind of hammering that same twist message that tells it to turn in place. If the robot doesn't receive a twist message in some amount of time, it will stop moving. And that's, I guess, like a safety feature. So it doesn't go drive off or run into something or run off a staircase. And so we just I've got a sleep of 0.1. So it's a delay in that loop. And then for 25 times for 0.1 seconds, it will publish a twist command. And then finally, whenever it finishes, I publish a twist command that turns the Z off. So it's just a blank one that tells it to stand still. And then it will go back through the loop and continue to execute that. At the end of this, I've got a couple of links here. So that's the end of these slides. Let's go back to the to this thing, and let's run this code. Let me also copy it to my clipboard so I can put it in here. Actually, I don't need to do that because I have already pre-built it and I just showed you the code, so I do not feel compelled to just rerun catkin for no reason. So let's detach this thing. Wouldn't surprise me. It's great. Okay. So then coming back over here, what I'm going to do is I'm going to call ROS run. And I had a package called beginner tutorials where I had my wanderer already created. And so when I run this, it will run that code we just saw. And it's now doing its thing. Let's see. Now, the one thing I'm waiting for it to just embarrass me as well is the Connect is not like the greatest sensor in the world. So it's, there we go. It's not going to see that chair. Oh my God. The chairs, it's the things that have like skinny legs. It's not doing a great job of picking that up, and they're just triggered on some noise. Anyways, the point is it's turning, and then is that an infinite loop? My God, I hate you. Wait, it kind of. Okay, so this isn't obviously the most intelligent code in the world. It just spins for an arbitrary amount of time, and now it's just spinning and continuously reobserving walls. So, but while it's doing that, let's look at a couple of things so we can see ROS topic, echo. We can look at the command velocities that we see getting published. So this was called CMD vel mux, I believe. ROS topic. Let me list them. Topic echo. Okay, so it's kind of slow input, and I'm publishing on the teleop topic. So we can see here my loop running in this. If you look on the z-axis of this angular twist message, you'll see some speed. Let's see if we can't free this guy from its eternal. Be free, please. I wonder if it's clearly it sees something. I wonder if it's. And I'm kind of wondering if it's seeing its own like body. It wasn't doing that earlier when I was testing it. That's the other thing about us. It's not very intelligent. I really should probably be examining the. That thing never stopped. Let me rerun the. No, that I did that. I'm just rerunning the node to see if it'll. Nope. See none. Oh man, I think this. Well, actually, we'll check it out here in a second. It looks like the node that runs the Connect has crashed because over here. Well, no, I was getting data before. We could always check that because I can just ROS topic, echo, laser, or it's just scan. We can see what's on that topic. Ooh, nothing. So yes, it is looks like it's died. Or let's see. I wanted to do ROS launch. So the other thing I wanted to show, I couldn't show last time actually because I couldn't get the network set up right, was doing the turtle bonnets, viz launchers, view robot. We saw it on the robot itself, but we can come here and we can see what the robot sees. Look at it. Wow. It knows it's spinning. And if I try to turn on the laser scan, we see nothing because it died. So maybe we'll boot it up just to finish this off so we can see that much. Gosh. Yeah, let's disconnect this crazy thing. Over here, should have just like SSH'd into it so I'd have a terminal open, but it ran this laser scan node literally all day, and I was very shocked. But I guess, now that it matters, doesn't look like it died. We got some other incoming velocity commands not received. Oh, that's fine. Let's just reboot this thing just come back here. Let me check. That seems fine. Make sure this thing. Where's RBiz now? Oh, see, there we go. We can see the laser scan in the back. There's also was this the one that, it'd be cool to see the depth map, but I don't think I had much success with that. I should not have checked one of those because RViz is now crapping itself. Okay, RViz, we'll come back to you in a minute. This doesn't work. I'm going to just call it a day. This one. See it all. No. See, we're running. Oh, okay. I think RViz died over here. That's okay. Pull it back up. Just let me see what the robot sees. It's gonna. Oh. Uh-oh. Oh wait, this is not checked. There we go. See, it's got some laser scan going on here. I think it's the image that looks kind of. Oh no, not the image. It can't see the. Oh my God. Well, hey, look, there we go. See, it finally saw it. As you can see from the see now, if you wonder, what's going on with your robot, we can look over here and we can see that clearly it thinks the path in front of it is just fine. And there's not a problem. Hey, James Briggs robot. Yeah, well, Ross is good. My equipment is bad, is what we've learned here. So when this sometimes you can get a better sensor than something that costs you $12 at Goodwill. But yeah, anyways, that's publishing and subscribing, everybody. If you want to run this horrible code on your own with your own TurtleBot that is outrageously priced, you can use the code that we have here. Everything that I used is on the you can find good tutorials if you're using a TurtleBot 2 at this link, and then the ROS Pi tutorials are here as well. And then of course, I've got, instead of leaving it there, I'll leave my QR code here. So this has the slides and the code as well. So you can grab that if you want. I'll go ahead and kill the recording here. Thanks everybody for coming. Thanks. Where's my